When it comes to buoyant force, there's three situations that we need to realize could occur. Most people understand the first two. They don't always fully understand what the third possibility would be. Everyone knows that if I place a mass in a fluid, it certainly may float. It also may sink. But there's a third case in which it will stay wherever I place it within that fluid. So if it was at rest here and I kind of moved it and dragged it a little bit lower and let go, it would remain at rest there as well. No matter where I place it in this fluid, it will stay at that location. And this specific condition is what's known as neutral buoyancy. It essentially means that the buoyant force that is trying to push you out of the water is exactly equal to the force of gravity pulling you down. So the buoyant force just comes from the fact that when you place one of these masses in a fluid, you essentially displace some of these fluid particles, and those fluid particles want to go back to their original location. The only way to do that is for them to attempt to push the mass out of the way, and in doing so, they generate this upward force that we call the buoyant force, and that's what we're going to take a look at today. In a situation where an object is floating, what you have is you have a buoyant force that is actually pushing the object up. That fluid trying to get back into that space that that mass is trying to take up is pushing back against that mass with more force than the force of gravity on that mass itself. Likewise, in a situation where the mass sinks, same concept, except the buoyant force of that fluid trying to take back that space is less than the force of gravity. So this should probably be a little bit longer here, I apologize, but the force of gravity in this case is larger than the buoyant force, and that's why this mass sinks. The last case is a special case with neutral buoyancy, and that occurs when the force of those fluid particles trying to push this mass out of the way and get back to their original location is exactly equal to the force of gravity pulling down. So it's like a balancing act. It's perfectly balanced, and wherever I let go of this, balanced forces will result in zero acceleration. So those are three different cases we can look at, but the question still remains, where does this actual force come from? Yes, it's the water molecules trying to get back in, but how can I calculate this? How can I use this to analyze different situations? And that all comes down to this concept. You have to realize that when I place a mass in a fluid, it displaces a certain amount of that fluid. So in this case, where the box is floating about halfway submerged, the area that is underneath the water has displaced that much water. So whatever volume is underneath the water has displaced that volume of water. So that volume of water that's been displaced has some kind of mass. And if I can find the mass of that water, I can find the force of gravity acting on that mass by using the acceleration due to gravity, 9.81 on Earth. But just realize that when it's half submerged, whatever volume of this box is underwater is the volume of water that has been displaced. Likewise, if the box is completely submerged, then the entire volume of the box is equal to the volume of water that was displaced. That's the key concept here, realizing that the amount of water that has been displaced is equal to whatever volume of the mass is underwater. And the way we can actually use this to find the buoyant force is that it is the weight of that displaced fluid that gives us the buoyant force. So if I can find the mass of this and I can convert that to the force of gravity that's pulling down on that mass of water, that is the buoyant force that's trying to push this block out of the way back to the surface so that water can take back its original location, or the fluid can take back its original location. Same here. If I can find the mass of the water that has been displaced, I can then find the force of gravity that acts on that, which in this case is the buoyant force. So the buoyant force is very simply the weight of the water that has been displaced. It's the weight of the water trying to get back into its original location. So Fg equals mg, so it's safe to say that since the buoyant force is the weight or the force of gravity of that water, you can find the buoyant force by multiplying the mass of the fluid that has been displaced by the acceleration due to gravity of whatever gravitational field you find yourself in. So I think the easiest way to go through this is to show you two quick examples. And we'll take a look at the first one. We know that this block has a mass of 80 kilograms and it has dimensions of 1 meter by 1 meter by 1 meter. We know that it's in water, and we know that the density of water is 1 kilogram per meter cubed. So the two questions we might want to find out is what buoyant force acts on this box, and what is the box's apparent weight? So as I submerge this box, the question becomes, it feels a little bit lighter. If you've ever kind of jumped into a pool or anything like that, you tend to feel a little bit lighter. And that's because this buoyant force is kind of trying to take some of the weight that you are used to feeling, and it tries to push you back up so you feel a little bit lighter. So the question then becomes, How can we find that? Well, knowing that the force of gravity acting on the water is the buoyant force, we'll start with that. So we know that the volume of the water that's been displaced is the same volume as the box because that box has been entirely submerged. So the volume of water that's been displaced is 1 cubic meter. We're given that the density is 1 kilogram per meter cubed. With these two variables, I can find the mass. So we know in this case, density times volume, I have 1 kilogram mass of water that has been removed. If I figure out the force of gravity acting on that 1 kilogram mass, which I've done here, I can find that the buoyant force, which is equal to that force of gravity of the water, is 9.81 newtons. So the answer to my first question is 9.81 newtons. That is the buoyant force that is attempting to push this block back to the surface. Now the question is, what is its apparent weight? What does it feel like? Well, it normally, when it's on land, feels 784.8 newtons, because that's what your normal force would be when this box is at rest. Found that by just multiplying the mass by the acceleration due to gravity. So this is what I would normally feel. But if I'm having 9.81 newtons kind of subtracted from that, my apparent weight is just going to be what the difference of those two is. I'm no longer feeling 784.8 newtons. I'm feeling a little bit lighter because, or this block is feeling a little bit lighter because it has this upward force that is attempting to make it feel as though its apparent weight, or the weight that it feels, is slightly less. The block still weighs 784.8 newtons, but if this was a person, they would feel a little bit lighter because they would perceive their weight to be about 774.99 newtons. And that's simply found by just finding the net force acting on this block. Just to show you another example, this is another more common example. You are given an unknown fluid, but you are given the density is 3 kilogram per meter cubed, and you're given that the dimensions of a block outside of the fluid are 2 by 2 by 2 meters, and it has a mass of 75 kilograms. So will the block float or sink? That's generally the question you will be asked. Well, hopefully you realize that it will sink if it has a greater density. It will float if it has a lighter density. So let's see if we can use this information to find what that density would be. The density of the block is quite simply the mass divided by the volume. So 75 divided by 8 would give me a density of 9.375 kilograms per meter cubed. That is certainly more than the 3 kilogram per meter cubed density of the fluid. Therefore, this block will absolutely sink. If I want to determine what its apparent weight would be, I'm going to have to figure out what the buoyant force is. So we know that since the block sinks entirely, we know that this entire volume will displace that entire volume of water. So the same volume of the fluid is the volume of the block, which is 8 cubic meters. The density of the fluid was given as 3 kilograms per meter cubed. I can therefore find that mass of that water that's been displaced. So I can find that there's 24 kilograms of water that has been displaced. Once I find that, I can use that to find the force of gravity on that block, the force of gravity of the water that's been displaced, which gives me my buoyant force. I can then use that to realize that the weight of the block minus that buoyant force will give me that apparent weight. So by finding the force of gravity on the block, subtracting the force of the weight of that water trying to push that block back up, this block will feel as though it weighs 500.3 newtons. It still certainly weighs as much as it did before, but it has this sensation of only feeling 500.3 newtons. The key thing to realize is that if you'd like to find the buoyant force, you need to find the mass of the fluid that has been displaced and multiply that by the acceleration due to gravity, because it is the weight of that displaced fluid that will give you the buoyant force.